Cycle 2, Lesson 5, Part 1, the logarithm. We've seen in previous lessons that a logarithm is an inverse of an exponential function. So if we have an exponential function in the form, say, y equals b to the x, then if we take the inverse of it, that would be x equals b to the y. We know that for any function, if we switch x and y, then we're going to get the inverse. So specifically, we can graph this. Let's just do that. So we have it to look at over here. Grab a Cartesian plane. Give myself a little room here. All right, so if I want to graph y equals b to the x, let's assume that it's growth. And so if it's growth, it's going to go upwards to the right. It's going to go through the point, the y-intercept of 0, 1, and then it's going to go up more or less steeply depending on what the base is. So that would be y equals b to the x. If I switch x and y, and I reflect my line, my curve, in the line y equals x, which looks like this, then we're going to get a reflection that goes through the x-intercept of 1, 0, and it's going to have a vertical asymptote on the y-axis, and then it's going to curve sharply to the right like this. And so that's the inverse of y equals b to the x. It's x equals b to the y. And that's also going to be represented by the equation y equals log base b of x. So these two here are inverses, not inverses, these two are equal to each other. X equals b to the y, that should say, and y equals log base b of x, equivalent. And they're both the inverse of y equals b to the x. So equivalent and inverse. So I think that's where we left it before. Remember, a logarithmic function is only defined like an exponential function for b greater than 0, and it can't be equal to 1. So here's some stuff that we can do just to play around with the equations of logarithmic functions. Well, actually not. Again, logarithmic and exponential are just different ways of writing the same relationship. So we're going to start with some exponential functions, such as, or exponential equations, to be even more correct. If I do 4 to the exponent 5, then that equals 1024. So that would be like the equation y equals b to the x. You know, if my x is 5 and my b is 4, my base is 4, 4 to the exponent 5 equals 1024. If I want to rewrite that in logarithmic form, then the equation still has to be true. It still the relationship still has to be true. So I can do that. I just have to put things in their appropriate places. So if we call this the exponent here, the 5, let's just zoom right in as much as I can. If 5 is the exponent and 4 is the base, let's use a different color. And there's a fancy word for what 1024 is. I forget it. I'm going to call it the answer for now. As in, what do you get if you raise 4 to the exponent 5? Well, the answer is 1024. I should remind myself of what that word is, but it's not coming to me at the second. All right, so if I want to rearrange this in logarithmic form, what happens is we get the exponent by itself, is equal to the log, and the base stays the same, so in this case base 4 of 1024. So all these parts are still here. So the exponent is now over here. The base moves down here from the log, and what I'm calling the answer is here. So if I take log base 4 of 1024, it equals 5. Another way of phrasing or thinking about this relationship is saying, what exponent do I have to put on what exponent do I have to put on 4 so that it equals 1024? When you look at it that way, you can think of logarithmic equations as being ones that isolate the exponent. All the parts are still there, but now we're isolating the exponent. So if this equation here, the next one is true, also exponential, it's saying, what exponent do I have to put on b so that it equals a? It just isolates the exponent. Well, we can tell from the way this relationship here is, we know the exponent we have to put on b is 7, so we'll isolate that. So 7 equals log base b. The base of the power is still the base of the logarithm, and the a goes here like this. So it's all about putting things in their right places. Again, what do we have here? We have an exponent, which we know is going to end up by itself over in this relationship. We have a base, which we know is going to be the base of the logarithm. And then we have the other part, which is what we're taking the logarithm of. So that's how you can rewrite something from an exponential into a logarithmic relationship. They're all still true, they're just in a different format. Logarithms to the base 10 are called common logarithms. When writing a common logarithm, it's not necessary to write the base. It's assumed to be a base 10. So, for example, log 100 is assumed to be a base 10. We could think of it as the same thing as log base 10 100. Since we got this one in our mind, we can now that we've done this part up here, we can start to think, well, what does that mean? Well, log 100 or log base 10 100 is really saying, what exponent do I have to put on 10 so that my answer is going to be 100? And so it would be 2. On our calculator, we should have a common logarithm button. Even this one on my iPad, which is not the best, should have a common logarithm button. It does. So if I were to do log 100, I'm just not sure what order. No, that's the wrong order. So if I go 100 log, there we go, it tells me 2. It's telling me that 2 is the exponent I have to put on 10 to equal 100. So let's put that into play with some examples here. Rewrite this in exponential form. Okay, so now we're just going the opposite way. So it's not specific. There will be some common log ones in here, but not specifically. This one's got a base of 4. So again, we have things like the base. What color did I use? I used red for the base and blue for the exponent. So base was 4, exponent, remember, is isolated in a logarithmic one, so the exponent would be 3, and then the answer, if I wrote it as an exponential, would be 64. So rewriting it, I can say 4 to the exponent 3 equals 64, because that's true. So it's just moving the parts around again, right? Exponent, well, I don't want to crisscross everything, but exponent, let's just base and answer, there, using the same colors. This one is a common log. It doesn't have a base written, so we know it's a base 10. So 10 to the exponent y, because y by itself is the exponent, equals x. So that's just going the opposite way. And then finally we can evaluate these things. So if we understand what it's saying, then we can We can use a calculator, but we can even just use some common sense. So we can say, what exponent do I need to put on a base of 3 so that it equals 81? So 3 squared is 9, 3 to the 3 is 27, 3 to the 4 is 81. So the answer has to be 4. What exponent do I have to put on a base of 2 to get an answer of 1/8? Well, to get 1/8, we need to know it's a negative exponent. 2 to the negative 1 would be a half. 2 to the negative 2 would be a quarter. 2 to the negative 3 is 1/8. So our answer for this one is -3. This one's given as a decimal, and it's a common log. So we know, again, what exponent do we have to put on a base 10? Let's actually write it out so we can see it better. What exponent do we have to put on a base of 10? And let's write this as a fraction. It'll probably be easier, as that's the same as 1 over 100. So what exponent goes on 10 to equal 1 over 100? Well, exponent of -1 gives 1/10, and the exponent of -2 would give 1/100th.